Hello there, fellow scientists. My name is Max, and this is Tea Time with Max. And today we're looking at an interesting problem in mathematics. It was actually part of my homework for maths. Consider the curve y equals x squared. Find the equation of a normal line to the curve at x equals c for any c being a real number. So when I look at a problem like this, which will take many steps, I like to break it down into small problems. So the first thing we're going to think about is, what is a normal line? So if you look at a graph of a curve, let's say a parabola, like we do have in our problem. So it looks something like this. It's going to come down and bounce back up. A normal line is a line that is perpendicular to the tangent of that graph. Now, what is a tangent? Well, a tangent line is a line that has the same gradient as a point on that curve. So for this point right here, this tangent line has the same gradient as that curve. Now, a normal line will be perpendicular to that. So there's going to be a 90-degree angle right here, and this is the line we are looking for. So now that we have that covered, and since we know we will be working with straight lines, it's probably a good idea to start with the basic equation for a straight line, which you might recall is y equals, let's use different colors, a, which will be the gradient of the line, times x, plus b, which will be the y-intercept. I know most of you will probably know this equation as y equals mx plus c. The letters don't really matter that much. The reason I used a and b in this case is because we have a c in our question, and if I put this as y equals mx plus c, we might have a bit of confusion later on because we're going to be using c for something else. So this will not be as useful for us, unfortunately, since we don't actually know what the y-intercept will be for that line. But we do know that the line will be passing for a certain point, and that point will be where x is equals to c. Okay, how does it help us? Well, let's consider a line which has the same gradient, but it passes through a certain point. Let's call that point x null and y null. So y null will equal to, the gradient is the same, a, x null is our x, and also the y-intercept, even though we don't know it, will also be that. Now, my cat decided to join us. You might hear him in the background. But either way, we can rearrange that to find what the y-intercept will be for this set of coordinates. We can simply write it as b equals to y null minus a times x null. Cool. So now we know for any given point with those coordinates, we can find out what the y-intercept is, and we can use that. In fact, we can plug that equation straight back into the first equation we had to figure out the equation of a line which passes for a certain point. And you will see that we don't actually need to know what is the y-intercept for that line. So let's plug that back in there. So y will equal to a times x plus this expression right here, which is y null minus a again x naught. Cool, we're getting somewhere. We can reorganize it to make it a little bit clearer. Let's get y's to one side. Y minus y null was equal to a times x minus a times, nope, that's not x, times x, nope. We can also simplify this, bring out the gradient in front of a bracket. So this is all equal to a times x minus x null in the bracket. This is a 0, by the way, or an O. I am not that good with whiteboards. Don't worry, don't worry. Okay, now we're getting somewhere. So now we know that this equation will give us a line which passes through a certain point y null and x null. We can now use that information, use that equation, to tackle our actual problem. So let's put it aside. Now what we have to figure out is, for our specific scenario, what is the gradient and what are the coordinates of our point. Cool. So we know that the x coordinate is equal to c, and c could be any number, any real number. And we also know that the y coordinate of this particular function is x squared. We can think about any generic function, and any generic function, a point on that function will be x and function of x. Because function of x, all it is it takes x as an input and it outputs y. So any point on that function will have the coordinates x and f of x. And since our x is equal to c, we also know that the y coordinate for that x at c will be c squared. So those are our coordinates, x and y. We'll be able to plug them straight into there to get our equation. Second thing, we've got to figure out what is the gradient of that line. And it might be easier to first find the gradient of the tangent line to our graph, and then from that figure out the normal line to the graph. And what is the gradient of the tangent line? As I explained before, a tangent line has the same gradient as the curve, and what that actually means is what is the rate of change at that particular point on the graph? How much does y change when x changes? And what is that? That's just differentiation. So we know that our function is x squared, and what is the derivative of x squared? It is equal to 2x. Sorry, old habit die hard. I used to write x like so, and then I was told that it looks like multiplication sign, which I agree. In Poland, when we learn multiplication, we use a dot as opposed to an x for multiplication. So that's why I got used to doing an x. Either way, we have now figured out, actually I should probably use orange for this, because this is our gradient. Actually, another thing. The gradient of that function is 2x. What is the gradient? What is the rate of change of that function at point C? Well, since x is equal to c, the rate of change at the point C will be 2c. Okay? So now we have everything we need to find out the equation for a line for a tangent. And from there we can work for the normal. So now we know that the equation for a tangent, I'm going to write it down, will be y minus, what is the y value for our scenario? It's c squared. That all equals to 2c, which is our gradient. And in the bracket, it's going to be x minus, what's our x in this scenario? C. So this is the equation for the tangent to our curve. Now, from that we can figure out the normal, because we know it's perpendicular to the tangent, and we know that any line that is perpendicular to another line, the gradient of that line will be the inverse, rather the reciprocal, that's also negative. The negative reciprocal of a gradient will give you a perpendicular line. What do I mean by that? If the gradient for a tangent is 2c, then the negative reciprocal of that will be minus 1 over 2c. It is inverted, it's also negative. So with that knowledge, we can now finally find the equation for the normal line to our curve, which will be, taken from here again, y equals, I should probably name it the normal, will be y, again, minus c squared, which is our y coordinate there. And that's equal to our inverse and negative value of the gradient of a tangent, which is minus 1 over 2c. That's the new gradient for our normal. And in here, nothing changes. X and our x value is c. Ta-da! And that is it. Now we have the equation for a normal for that specific curve. But guess what? We can take it further. We can find a normal and a tangent to any function that we want. Because all this is, I should probably move to this side, all this is saying that f of x, again, old habits die hard. Oh my. There we go. All that is saying is that the function of x is x squared. We plug in number x and we get out an x squared. So if our x is 2, our x squared is 4, etc., etc. This function could be anything. It could be x squared plus x minus 4. It could be sine of x, whatever you like. So let's generalize what we just done here. You're still going to be using this here because we're looking for a line. What actually is our x coordinate and our y coordinate for any given problem? Well, just like here, we realize that for x equals c, the x coordinate will obviously be c, right? And now what is our y coordinate? Well, we're using a function. We input an x and we get y in return. So actually, the y coordinate of any given function at point C, which could be any number, will just be function of c, right? So for example here, at x equal to, the function of x will be equal to 4, 2 squared. So the coordinate for any given function will be just that. C, or whatever other letter you like to use, and function of that same letter. Okay, but what is the gradient? What is the gradient of the tangent? Well, we figured out that gradient of a tangent line is basically the rate of change at that point of any given curve, and that is just a derivative of that function. So in fact, the gradient of any given function of a tangent will be the first derivative of that function, right? This will be the gradient of a tangent. And since we're using c, x equals c, this will be our gradient for our tangent, right here. Okay, we can follow it further. What about the normal line? Well, we know that the gradient of a normal line is the negative reciprocal of the gradient of a tangent. So all it is basically minus 1 over the derivative of function at point C. Right there. So getting it all together now, we can figure out that for any function whatsoever, this could be anything, the tangent line for that function will be equal to y minus f of c. That's our y value, as we figured out. Okay. And that all equals to our gradient, which is just the derivative of that function. So the first derivative of function at point C. And in the brackets, we have value of x minus, right here, c, since x equals to c. And this is the general equation for a tangent to any function you can imagine. And with the same logic, we can conclude that for a normal line to a curve, we can follow the same logic, but now instead of the derivative of the function, the gradient will be the negative reciprocal of that function, which is that. Can you tell I'm having troubles writing that in that direction? Less. And obviously in our brackets we still have that. So there you have it. Not only have we figured out the tangent to our specific case, to our specific function, also the normal in our specific function, but also we found how to figure out the tangent and the normal line to any given function whatsoever. You can plug these into Desmos and set c as a variable, and you can animate it and you can see the lines basically sliding on your function. It's really fun. So yeah, there you have it. I hope you learned something. I definitely did. It was really fun to figure out. And yeah, I suppose I will see you very, very soon. Bye bye.